Hello everyone, with great pleasure I shall welcome you all once again to MSB lecture series on interpretive spectroscopy. In my last lecture I started talking about UV visible spectroscopy, so let me continue from where I had stopped in my previous lecture. We started talking about electronic transitions. Of course, electronic transitions can be broadly classified into 4 types: sigma, sigma star, n to sigma star, n to pi star, and pi to pi star. And sigma to sigma star are shown by saturated hydrocarbons in which all valence shell electrons are involved in the formation of sigma bond. That means no electrons are left unutilized for bond formation in the valence shell. So these transitions require very high energy and occur at lesser wavelengths, less than 200 nanometer, and fall in vacuum UV region. And if we consider n to sigma star transition, compounds having non-bonding electrons on heteroatoms such as oxygen, nitrogen, sulfur, or halogens can show such type of transitions. The energy required for these transitions decrease with the decrease in electronegativity of heteroatom, and therefore the wavelength of absorption increases. And then the third type is n to pi star. Compounds having double bond between heteroatoms, for example, C double bond O, C double bond S, N double bond O, etc., show these kind of n to pi star transitions. These transitions requires only small amount of energy and takes place within the range of ordinary ultraviolet region. However, the intensity of absorption is generally very low, and these transitions have an epsilon value of less than 10 raised to 4. Of course, here when you look into overall the energy difference between these levels, n to pi star is the least energetic. That's the reason it requires very low energy for the promotion of the electrons. Pi star, compounds having double bonds show these transitions. The intensity of transition is very high for these transitions. These transitions have epsilon value in the range of 10 to the power of 4 or more, and they are also allowed transitions. All these electronic spectroscopy, if you look into it, all these compounds having different region of UV visible range. So that means definitely we have substituent effects. So what are those? A functional group capable of having a characteristic electron transition is called a chromophore. We should remember the chromophore is responsible for electronic transition. The attachment of a substituent group other than hydrogen can shift the energy of the transition. So that means substituents that increase the intensity and often wavelength of an absorption are called oxochromes. And then substituents may have any one of the 4 effects on chromophore. Okay. What is that one? We call it as bathochromic shift. That's also known as red shift. What happens in this one? Shift to longer wavelength. When it goes to longer wavelength means probably we are thinking of decreasing the gap between HOMO and LUMO. So then it requires low energy. That's the reason it's called bathochromic shift or red shift, or shifting to longer wavelength, or it's a low energy transition. Then the second one is hypsochromic shift. That's also called blue shift. That means shifting to shorter wavelength and higher energy. That means when the gap increases, we need to give more energy. That's the reason it's called blue shift, and also shift to shorter wavelength and also high energy transition. What is hyperchromic effect? An increase in the intensity of the transition. Then hypochromic effect is a decrease in intensity. So these 4 terms we come across, and these 4 comes as a consequence of the influence of substituent on chromophore. You can see here in this plot, you can see if you say here it's a 200 nanometer and here 700 nanometer, and this is epsilon value, you can see hypochromic and hypochromic, this is hyperchromic, and this is hypochromic, and this is bathochromic and hypsochromic. The moment you see the shift from left to right, it has to be hypsochromic blue shift, and right to left means it is bathochromic red shift, and also intensity is going high, it is called hyperchromic, and intensity is dropping, it is called hypochromic. So these are the influence of substituents on chromophore, which is responsible for electronic transition. So now here I have given a list of chromophores and with a specific example in each case, and also the solvent in which we have looked into the transition and the lambda maximum and epsilon and also the type of transition. Very useful table this is. For example, if you look into alkene, we know that we have a double bond. So immediately we can say it should be a pi-pi transition, and once it is a pi-pi transition, you can anticipate little higher epsilon value. This is in the 13,000 and lambda maximum is 177 nanometer. The solvent considered is N-heptane. Then if we take alkyne, we have a triple bond, and again solvent used is N-heptane. It can show lambda maximum in the range of 178 to 225, and then here epsilon value varies 10,000, 2,000 or 160, and here it is pi-pi star transition. Other transitions can also be seen. Okay. And then if you consider carbonyl groups make aldehyde, acid or a ketone. So in this case, for example, if you consider aldehyde, N-hexane is there, and here you can anticipate 186 as well as 280, and for 186 epsilon value is little higher compared to 280, it's low. And then for this acetone, N-hexane, 180 and 293, and in case of 180 large epsilon value will be there, in 293 it is low, and here and the large one is due to N2 sigma star and the lower one is due to N2 pi star. We know that N2 pi star is of weak intensity, and same thing here. Whenever a weak intensity is there, you can conclude that it is not N2 sigma star, it's not even pi to pi star, it is N2 pi star. And then carboxylic group, if you consider acetic acid an example recorded in ethanol, it shows 204 and then 41. So immediately when you look into the epsilon value, one can conclude that certainly it is due to N to pi star transition. And in case of amido group, for example, if you take acetylamide, water is taken as a solvent because it's soluble in water. This is 214, and then 60, again same thing, it is N to pi star. And then with azo compounds are there, N double bond N ethanol and 339, and then 5 very low. So again you can conclude that it is N to pi star. In case of nitro, isooctane is a solvent taken and value is 280, and epsilon value is again low, 22. So this also again due to N pi star transition. If you take nitroso group recorded in ethyl ether, 300, base are 100, whereas in case of 665, 20, it is again N to pi star. And then in case nitrate, it is dioxane is the solvent chosen, and then lambda maximum is 270, and then epsilon is very low again. So what we can see clearly is pi to pi star has higher epsilon value, and N to sigma star also has reasonably higher epsilon value, but wherever the epsilon absorptive coefficient is very low, without any hesitation we can tell this is due to N to pi star transition. This gives some idea about the different type of chromophores and their characteristic lambda maximum and epsilon maximum, and also the type of transition we come across. Then after looking into substituent effect, let's look into solvent effect. Solvent effect, when we talk about the polarity comes into the picture, increase in the polarity of the solvents shifts N to pi star transition to shorter wavelength. That means addition of polar solvent results in blue shift. N to pi star goes to shorter wavelength or higher energy. That means gap is increasing. So this blue shift is mainly due to the greater stabilization of the ground state than the excited state through dipole-dipole interaction. That means polar solvent induces dipole-dipole interaction. As a result, what happens? The ground state will be dropped in energy than the excited state, and hence the energy gap increases and the wavelength decreases and the energy required increases in frequency. So this is a typical polar solvent. For example, when you take non-polar solvent, this is the situation when you add a polar solvent, the ground state is more stabilized, it means it drops in energy. As a result, N pi star gap, HOMO-LOMO gap increases, and hence it shifts to blue region. It's called blue shift. That means if a group is more polar in the ground state than in the excited state, increasing the polarity of the solvent shifts the absorption to shorter wavelength. So this we should remember, we come across. hypsochromic shift, blue shift. On the other hand, increase in polarity of the solvent shifts pi to pi star transition to longer wavelength, then it's called red shift. So the red shift is mainly due to the greater stabilization of excited state than the ground state through dipole-dipole interaction. Formation of hydrogen bonds or solvent effect with the polar solvent is responsible for this kind of rearrangement. So that means increase in the polarity of the solvent brings down the pi star gap to the lower level. As a result, what happens? Longer wavelength radiation is required for electronic transition. This is called red shift. Red shift is mainly due to the greater stabilization of the excited state than the ground state. In case of earlier one, we saw the blue shift is mainly due to the greater stabilization of ground state than the excited state. Opposite is true here. The red shift is mainly due to the greater stabilization of the excited state than the ground state through dipole-dipole interaction. This is probably due to hydrogen bonding or solvation with the polar solvent. So you can see the situation in non-polar solvent, this is the one, and in the polar solvent this gap decreases and it goes to red shift, that means longer wavelength. That means if a group is more polar in the excited state than in the ground state, the increasing the polarity of the solvent shifts the absorption to longer wavelength. This is the second type of solvent effect on pi star transition. Previous one was N to pi star transition. Then what would happen if there is an extended conjugation? An increase in conjugation decreases the energy required for electronic excitation. That means extensive conjugation brings the gap between pi star. If the pi is HOMO and pi star is LUMO, this gap is considerably brought down if we have extended conjugation. From molecular orbital diagram shown here, two atomic p orbitals form two sets of sp2 hybrid carbons here and here, so form pi star in ethylene. So here you can see this is simple ethylene, but if you compare this one to butadiene, here mixing of 4p orbitals results in energetically symmetrical distribution of 4 MOs compared to ethylene, due to which HOMO-LUMO gap is reduced and hence transition energy goes to longer wavelength. So that means you can compare here, this is for typical ethylene and this is for butadiene here. The gap is considerably lower here compared to what we see in case of ethylene. So that means delta E or energy required for HOMO-LUMO transition is reduced here. That means conjugation decreases the HOMO-LUMO gap and hence it will be a red shift. So conjugation effect can be seen for different transitions here with the different systems. The longer conjugated systems decrease the energy gap between HOMO and LUMO, and it progressively becomes smaller and absorption shifts to longer wavelengths. So you can see here ethylene to butadiene to hexatriene to octatetraene. So that means you start from one double bond, two double bonds conjugated, three double bonds conjugated and four double bonds conjugated. You can see very nicely the energy gap is diminishing and shifting towards the longer wavelength. So this is called conjugation effect. So now let us look into important rules such as Woodward-Fieser rules for calculating lambda maximum for a given compound by considering all functional groups present in it. If you consider homoannular diene, a cyclic diene with conjugated double bonds in the same ring, they are called homoannular diene. If you have conjugation or conjugated double bonds in the same ring, this is called cyclic diene. And then we look into heteroannular diene, a cyclic diene with conjugated double bonds present in different rings. It can be something like this or it can be something like this. So heteroannular diene is one in which we have a typical cyclic diene with conjugation or two double bonds present in different rings. And endocyclic double bond, a double bond present in a ring is called endocyclic double bond. Exocyclic double bond, a double bond outside the ring with one of the doubly bonded atom is a part of a ring. So this is something like this. And here we have both endocyclic double bond and exocyclic double bond. This is a typical example here where you have both. So this is how some of these unsaturated compounds are defined with terms homoannular diene, heteroannular diene, endocyclic double bond and exocyclic double bond, with example in each case is given here. What are the Woodward-Fieser rules for conjugated dienes, trienes, polyenes, etc.? Let us look into it. Let us consider a parent value. So by identifying the type of cyclic system, we have to give a parent value What are those parent value? Acyclic conjugated diene, the value is 217 nanometer. For homoannular conjugated diene, it's 253 nanometer. In case of heteroannular conjugated diene, it's 214 nanometer, we should remember. Now we should look into the increment provided we add something else to it. For example, each alkyl substituent or a ring residue add 5 nanometer, and each exocyclic double bond we should add another 5 nanometer, and then double bond extending conjugation 30 nanometer. If we have oxochrome such as OR 6 nanometer and SR 30 nanometer, and if you have OCOCH carboxylic group, then there is no need to add anything. And if you have chlorine or bromine, add 5 nanometer, and if you have an amide group NR2, add 60 nanometer. So one typical example is given here, and calculated value here comes 234 nanometers by considering the heteroannular diene here, and then the 3 ring residue is there. So add 1 ring is 5, so 3 are there, 15, and 1 exocyclic double bond is there, another 5 increment. So it comes around, calculated lambda maximum comes around 234, and if you actually measure, it would come very close to this value given here. Then if you see homoannular diene conjugation within the ring, the value designated is 253, and 2 ring residue, so 10 nanometer, 2 alkyl substituents 10 nanometer, it comes around 273 nanometer. So this is how one can effectively use Woodward-Fieser rules for conjugated dienes to predict the lambda maximum value. Okay, now further continue. If we have alpha beta unsaturated compounds also, Woodward-Fieser rules are available. Parent values are given here. Alpha beta unsaturated acyclic or 6-membered ring ketone, the value is 250 nanometer, and alpha beta unsaturated 5-membered ring ketone is 202, and alpha beta unsaturated aldehyde is 207 nanometer is the parent value. And then increments follow this order. At alpha position, if you have alkyl substituent or ring residue, then add 10 nanometer. At alpha position, okay, at beta position, add 12 nanometer, and at gamma and higher position, add 18 nanometer. And for every exocyclic double bond, add 5 nanometer, and double bond exocyclic to 2 rings simultaneously, that's at 10 nanometer. So that means we have to watch carefully the structure before we give this increments for the parent value. And then double bond extending conjugation give 30 nanometer, and homoannular conjugated dienes at 39 nanometer. So one such example is considered here. Parent value is 215 here, because this is alpha beta unsaturated 6-membered ring here. And then one alpha ring is there, 10 nanometer, and one delta ring is there, 18 nanometer, one exocyclic double bond is there, 5 nanometer, one double bond extending conjugation 30 nanometer, one homoannular conjugate diene is there, 39 nanometer. So calculated lambda maximum value for this compound, considering the increments added to the parent value, it comes around 317 nanometer. So one can conveniently use this method to predict the lambda maximum value, and then that can always compared with the experimental value. So here some oxochromes values are given. If alpha position for hydroxy group 35, beta 30, and gamma 50, and similarly for OR group, alkoxy or alloxy group 35, 30, 37 respectively for alpha, beta, and gamma positions. And if we have SR value, SR is there, functional group. So in this case, what happens? Alpha nil, beta it's 85, and gamma nil. And if you have carboxylic group, alpha position 6, beta also 6, and gamma, whether it's in alpha, beta, or gamma, 6 increment has to be given nanometer. And for chlorine, alpha position 15, beta position 12, and nothing need to be added if it is in gamma position. And then similarly for bromine, we add 25 and 30. So this is how we can carefully look into the increments by identifying the groups and their position, and adding the increments for various oxochromes or other fragments to the parent value. Very conveniently, very nicely, very precisely we can calculate the lambda maximum value. Now let's look into the type of electronic transitions responsible for color of compounds, especially coordination compounds. So that means in complexes, instead of looking into the several transitions I showed you, most of these transitions, whatever I showed you, sigma to sigma star, pi to pi star, n to pi star, n to sigma star, these are all mostly confined to organic moieties. Nevertheless, we can also see in the metal complexes originating from ligands or metals to an extent, and we get one more extra transition, that's called DD transition in metal complexes. For example, if you consider 3D, 4D or 5D series, they have anywhere from D1 to D10 electrons in their valence shell. And then in case of octahedral compounds, we know from crystal field theory that they are split into T2G and EG. And in case of tetrahedral complexes, it's E and T2, opposite of that one. And in case of square planar complexes, we have DXY as HOMO and DX minus Y square as LUMO. And between them, electron transition takes place, that we call it as DD transitions. So what are the conditions for DD transitions? Do really DD transitions are allowed or not? All those things we shall look into in detail in my next lecture. Now, just I have given one example here, hexa-aqua titanium 3 plus a D1 system, and here you can see when the electron is there and this electron, after giving the energy, it is promoted here. This is called DD transition. Similarly, if you take cobalt, tetrachlorocobaltate 2 minus, it is tetrahedral compound. We have 4 electrons, it's a high spin complex. We have 4 electrons in E and 3 electrons in T2. So here, which electron is responsible? So either this electron can go or this electron can go. That's what we have seen. So here we can see the transition. So let us look into more details of DD transitions in my next lecture. So until then, see you all. Have a nice time.